Today we're going to look at some of the theory, the content that you were to watch. We're going to use some of this to prove something or show something here. And this problem, you've seen this on the Newton's method, approximating a solution. But we're going to show that that solution you approximated is the one and only solution, real solution. There's a theorem in algebra that says this actually will have three solutions because it's a cubic equation, but we will only be able to find one real solution. The other two solutions would be complex solutions. We're not going to go there today, but really this statement show that this equation has exactly one solution. There's really two parts to prove. First of all, show that it has at least one solution, and then show that there is only one solution, or what we say, the solution is unique. So, first step, show that it has at least one solution. It has. And this can be done with some algebraic ideas. You may have actually seen something like this in an algebra class. But from the intermediate value theorem, the idea here is when we look at the function, let's see, f of 0, plug 0 in for x, and we get what for the function value? Okay, we get a -1. So at x equals 0, we're at -1. And then, well, this one kind of worked out nice. What if x is +1? What do we get for y? Okay, +1. And I emphasize the positive there. At 0, we'll have a negative function value. At 1, we'll have a positive function value. Now, the calculus side of this is the intermediate value theorem says if we have a continuous function, and going back to that idea, any of our polynomials, x squared, x cubed, x to the fourth, anything like that, those terms added together will be continuous. So we do have a continuous function, and then the idea, we could take a quick look at the graph. F of 0 is -1. When x is 1, y is +1. And the graph is continuous. That means we need to connect the dots somehow. Okay, and could go up and back down and back up as long as we get through both of those points. Okay, or as in this particular case, we can't prove it just yet, but this is what we're proving. It may do something like that. But there is at least one point between x equals 0 and x equals 1 that we get a y value of 0. which graphically means x-intercept. Now, what we've shown, it may be 3 different values. Okay? Intermediate value theorem just tells us we can say it is an existence theorem. There exists one. There may be 2 or 3 or many more for that matter, but there is at least one x-intercept as long as one of the values is negative, one of the function values is negative, and one of the function values is positive. There's at least one place where the function value is 0. Okay? So that shows not so much exactly one, but at least one. Questions on that? Now the last part to this problem, show that there's exactly one solution, is show that there is only one solution. Or actually we should put real solution in here. We've shown that there is at least one. Now we're going to show what we call the uniqueness of the solution. There is a unique solution. There is only one solution to this equation, one real solution. Now this gets into a lot more kind of heavy theory that the intermediate value theorem is a theorem, but it's a little bit easier to see and to work with. What we're going to be looking at to show this last part is using Rolle's theorem. And he talked about that in the videos. We'll look specifically at what it means. And this also kind of introduces you to a technique of proving something. Some of you may actually be math majors, or especially after having me, you want to be a math teacher. Well, or in spite of having me, you still want to be a math teacher. Maybe that's the case. But you've got to be able to prove things, not just, well, it looks like that's true, we'll take that for granted. No, we've got to be able to prove stuff. And this is not that you need to be able to do that right now at this point, but as you take upper level classes, you'll be asked to show or prove that something is true. Now, this technique that we're going to use for this one is called an assumption. We're going to assume something, and then we're going to show that with what we know, the assumption is wrong, which means the opposite of the assumption must be the case, or, well, kind of that idea. So, let's show that, or we will assume that there are 2 solutions to this. And we can even get more specific. We know the solution must be, well, yeah, we don't need to be that specific, but we know there's a solution between 0 and 1, so we're going to show that there's exactly 1 by assuming first there's 2 solutions in there. So we're going to let x equals c sub 1 and x equals c sub 2 be these 2 solutions. Now, what that means is f of c sub 1, f of this particular x value is going to equal 0, and f of c sub 2 is also going to equal 0. That's another way of stating this in mathematical terms. So let's show that. F of c sub 1 equals 0, and f of c sub 2 equals 0. And our assumption, c sub 1 is not the same value as c sub 2. They have to be different if we're going to show or assume there's two solutions here. Now, by Rolle's theorem, you may not remember all the details of it. I'll explain that as we go. Rolle's theorem says that if f is continuous, which we already said we could show, we've talked about continuity before. If f is continuous and, well, differentiable, that means the derivative will exist. Differentiable. The derivative exists, and for these polynomials, we could show the derivative exists everywhere. We could find that derivative, which we will here in a second, but there's no place where the derivative would not exist. An example of where it would exist is if we had, or where it would not be differentiable, 1 over x, x equals 0. If the derivative was 1 over x, then x could not be 0. But with polynomials, they work a lot nicer, and f is differentiable for all x values. Now, here is one key part to Rolle's theorem. F of c sub 1 must equal f of c sub 2 for us to be able to state this. Now, with those conditions, continuous and differentiable function, and f of c sub 1 equals f of c sub 2, which we identified them as x-intercepts, where the equation would equal 0, or where the function would equal 0. Rolle's theorem says there is at least one x value in the interval I guess we could say this. Now, we really have not said that c sub 1 needs to be smaller than c sub 2, but we could assume that. Okay, the point here, x has to be somewhere in between c sub 1 and c sub 2, such that f primed of x equals 0. Okay. Now think about that. We have two numbers, two x values, that the y values are 0. And graphically, if we have a continuous function, if it's going up from the first 0, from c sub 1, okay, to get back to the second 0, c sub 2, the graph has to turn around to be able to go down to it, which means there's some point up there where the derivative, the slope of the tangent line, would equal 0. Okay? Or perhaps the graph may be going down through C sub 1, but to get through C sub 2, it's got to turn around and go back up. So again, somewhere where that graph turns around, the derivative is going to equal 0. Okay. Now, that's based solely on our assumption that we do have two solutions. And using Rolle's theorem, the function fits nicely, it's continuous, it's differentiable, and our assumption C sub 1 and C sub 2 have y values that are the same. Okay. Now, let's take a look at the derivative. With our function being x cubed plus x minus 1, what's the derivative? Three x squared plus 1. Okay. And what happens when we try to set this equal to 0? Based on our assumption, Rolle's theorem must be true. However, what happens when we try to solve this? What do we get when we square root a negative? Turns out to be complex numbers, not a real number. So what we find out really is that the derivative, looking over the entire function, not just between 0 and 1, but we can look at this for the entire function, the derivative is going to be greater than 0 for all x. Okay. Because of the plus 1, and then we're squaring the x value. Any square of a number is going to be positive or equal to 0. But with the plus 1, the very smallest value we'd end up with for a derivative would be positive 1. Everything else will be larger than positive 1. So we're never going to find a point where the derivative equals 0. Well, that kind of throws out Rolle's theorem. Did Rolle get it wrong? No, Rolle's theorem is correct. What is incorrect is our assumption. What did we assume? Our assumption that there are two solutions must be incorrect. So, what's that tell us then? There's only one solution to the equation, one real solution. Always have to throw that in there. To the equation x cubed plus x minus 1 equals 0. Actually, Rolle's theorem tells us there's less than 2 solutions. Okay, there's not going to be 2 or more solutions. There's less than 2 solutions, which means it could be 1 solution or 0 solutions. But we had already shown with the intermediate value theorem, there's going to be at least 1. So putting the intermediate value theorem and Rolle's theorem together, there is exactly 1 solution. If I could spell, that would help. Now, we don't spend a lot of time with the theorems and proving stuff, but it is good for all of you, even if you're not going into math, it is good for all of you to see some of these theorems, proofs worked out once in a while. Question?
Then what is the real solution?
Okay, what is the real solution? Well, that is sometimes not able to be found exactly. And in this particular problem, let's see, there is a cubic formula like what we do with the quadratic formula solving a quadratic equation. There's a cubic formula. I have never worked with the cubic formula, but I know it exists. So we could find the exact solution using that cubic formula. Some equations, and in fact a lot of equations that you will run into in the real world, you're not going to be able to find an exact solution. That would take the appropriate either calculus or algebraic technique, and quadratic equations are probably the easiest ones. We do know how to find exact solutions there based on the quadratic formula. There is a cubic formula. I think even there's a quartic formula, a 4th degree polynomial set equal to 0. Again, I've never worked with it before, but I think it exists. I'm not sure about a 5th degree. I think they're still working on that. That's what the people with PhDs in mathematics, they work on things like this. But anything beyond 5th degree, they have not found any nice little formulas to use. And that's just with polynomials. And polynomials, they seem to work nicer than most every other function. An equation involving, say, a trig function, sine x plus x equals 0. Have fun with that one. I don't think there's any way we can find an exact value for that. Well, there is one way. X equals 0 would work on that, but is there any others? Okay. Or some combination like that. You can kind of get the idea. You're probably not going to be able to find an exact value. But using Newton's method or some other approximation technique, you can at least find a value up to 5 decimal places or 20 decimal places, or with the right computer program you could find it to 100 decimal places, which is more likely good enough. In the real world, that would be more than good enough. So some good questions, good things to think about, and so now you've seen that we can find, or that we can show there's exactly one solution here, but we may not be able to find the exact value of it. Okay.